is up, people? So, I'm a little less angry today. I'm a little happier today. In fact, I'm not gonna lie to you, it's a great fucking day. So, with that said, we're gonna go ahead and do a gravity simulator. So, I'm not sure if you guys know exactly what this is. Basically, it simulates. He'll explain it because I suck at explaining anything. But I will tell you right now, the second you see it, you probably will recognize it right away, and you probably will have tried it before. I know I have probably 20 to 30 times in the past 36 hours, and I'm not really, I don't know what to do. Everything just flies into space, and goodbye. So we're going to learn how to figure that out and get some key points to what these models are, these simulators are. Bernie, I appreciate you taking the time to do this. I know it's not just a simple here you go. So everyone in the chat, just to kind of understand, he's going to be explaining things. He wants to make sure it's understandable. So if we do you get to a spot and you don't understand where A and B happened at, let me know in the chat. I'm here, I'm looking at it, and I will let him know. But he didn't say this, but I'm saying this. I can't do 20 stops in a minute because then the live stream will be 8.5 hours. So bear with me on that one, and just understand that it's learning time. I'm not sure how I feel, but most likely we'll continue after. I got some fun stuff to talk about, and even more importantly, the fun stuff that I like to talk about. I got some fun excuses that I've been hearing over the past 2 days with what happened yesterday. It's interesting. It made me laugh. I'm in a good mood because of it. So, Bernie, my friend, take it away.
Hello, can you hear me now? Somebody in the live chat.
Okay, so
confirm that you can hear me.
Hang on, I'm gonna check it right now on my side, because I was hearing you on my end. Give me 2 seconds, and then it'll catch up to us.
No problem.
Okay, I see what it was. I had a filter on. I apologize.
Okay. Hello,
yep,
can you hear me now?
We're good to go. They got audio now. Sorry about that, guys. No. It was my mess up. I had a filter on one of my audio ends, and I forgot to take it off. Apologize.
Now that I've given the best intro monologue that you have ever possibly heard, and that your hearts are all up in.
Yeah, I mean, all the flat earthers would have already dropped their pants. It would have happened. I heard it.
Okay, so once again, in brief lines, the point of this is just to transparently go through the process of applying a model, of taking the Newton's formula for gravitation and demonstrating how to apply it in code so that it works, that everything is there, that you can see for yourself the results, that you can get a functioning simulation that can then be used to compare with observation. To be clear, I will not be doing anything about observations today. This is more of a demonstration of a process of creating a simulation. This is not intended to prove anything or disprove anything about globe Earth or flat world. It's that part really doesn't come into it, even though we may touch upon why I believe some things that I believe. This is more of this is how we do it. This is how a model is used to demonstrate things. So usually these things are programmed either in physics laboratories and like on colleges, and people use them to demonstrate or to test out ideas about orbital fluid mechanics, or more commonly, they're written as physics simulators in video games. And in both of those instances, the thing that gets most most attention is optimizing it, making it run as quickly as possible by using as little resources as possible and doing all the math tricks that are available to make it as efficient and as precise as possible. I'll be foregoing all of that. I'll be using kind of the worst possible method, the algebraic method for solving Newton's formulas. Basically, substituting. We won't be doing calculus. I won't be doing calculus. It'll just be addition, subtraction, multiplication, division, potentiation, and practically nothing. A little bit of trigonometry, but more or less elementary school stuff. And I'll be substituting that with raw processing power of my laptop and just telling it to do everything. So it'll be a very bad program programming-wise. The thing that I'll be focusing on is making it clear. So making everybody who sees this understand what each and every little thing does and why, without knowing higher maths or knowing programming themselves. So if at any point it becomes hard to follow or it becomes a problem, then I'm failing at what I'm trying to do and I want to be stopped. So please at me in the live chat. I have it up. So, and yeah, of course, the idea is to kind of answer as many questions and make things as simple as possible while staying on this one very narrow topic. So, right, I won't be answering questions that have nothing to do with that one formula or how it's applied. Maybe I will. I love talking so much that I can't stop myself, but the goal is not to get off topic. Okay, so I'll be starting literally from scratch by opening a blank file and hopefully sharing it on screen at some point. Share screen, this thing, share, and present to everyone. That should be it. And we'll need a browser window. So we'll use this one and we'll. Okay, what are we doing? We're solving the gravitational formula. Gravitational formula. This is the one. So we have. Do we have a copy pastable example? No. Is it an image? Why is it an image? Come on, I want text. Never mind. So the force is equal to the gravitational constant, the masses of the objects, multiplied by the masses of the objects, and divided by their distance squared. Okay, and that's our start. So F equals G times M1 times M2, everything divided by R squared. We can do it. R squared, right? Syntax, whoops. Oh, out. Syntax, JavaScript. Oh, and I'll be using JavaScript just so that this is something that you can literally do with Notepad and then run it in your browser window. So no technology, no installations required. Okay, so this is the formula that we'll be solving. Force G. Okay, we need to define G. G is the gravitational constant, var G. Let's Google that one. Gravitational constant is this thing. Equals this thing. Okay, we'll just turn it into notation, write it down in the form that the computer will recognize. So, E minus 11. Okay, so it's some really tiny number. It's 0.10 more zeros, and then 6, 6, 7, 4, 8. So tiny. Oh, one thing. I'll be using metric just because that's the way I think.
Well,
I'm European. I grew up with metric.
well, we may not understand metric so well, but we know how to Google.
Yeah, these things can get converted. One thing about the gravitational formula of the natural constants, there are two kinds of constants. One constant is stuff like pi, which is always the same. Whatever you do to it, it's always the same. And the other ones are relational constants, such as these. These constants are basically numbers that are limited by our definition of what a meter is and what a kilogram is and what a second is, and kind of create a way for them to combine in a meaningful way. For every such constant, there is a set of natural units, and those are usually either Planck units or light-based units. So if you take the gravitational formula in metric, it's this. If you take it in imperial, it'll be a different number because these units will be changing, because this is meter and it'll be feet, this is kilogram and it'll be pounds, right? So this number will change. But if you do it in Planck's units, gravitational constant is just 1. So it doesn't even come into the equation. Okay, so we have our first thing. Next thing, mass 1. So that'll be Earth. We'll need an object. Earth is an object. And that object will have a property of mass. And we'll need moon, which will be an object. And it too will have some mass.
And how are you coming about your calculation for the mass? Is that just the standard numbers?
We'll for the purposes of this, all the input data I will just Google.
Okay.
So I'm assuming that some other scientists have found those things, and I'm just creating a simulation based on the available data. Now,
mainly because of time constraints, right?
Mainly because of time constraints, but in any situation I would be doing that. I would just be looking for a more precise set of data, right? Because these things are kind of abbreviated.
Yeah.
But
that would have been more of a problem for earlier times.
It would, but not so much. So the thing about these things is that you can work with imprecise data. You can estimate and be within some error margins, right? A certain range of values, and say, good enough. And you'll see a lot of that. Like I won't be using more than 3 or 4 significant figures here. Nor will I be carrying, right? If it's, I don't know, you'll see, right? The deviation is not that much. However, if the formula is wrong, then the deviation will come up and show up, and I will know that there is either something wrong with the data that I've input, or there's something wrong with the model that I'm using.
Yes. Okay.
And those things can then be used to say, oh, there is a problem. Let's find and identify the problem. Do better measurements or find a better model. If you cannot get better measurements, you will ultimately have to say, like, if you get better and better measurements and the problem persists, you will ultimately have to admit that your model is flawed.
Oh, okay, I see. Understand.
Okay, so we need the Earth mass. Mass is this thing. So it's 5, 6. 6 times 10 to the 24th. And moon mass more significant figures. This is potentiation, I'm guessing. So this to the power times 10 to the power of 27. So this E notation, when you have a number and you have E some other number, that's times 10 to what power? So literally, how many zeros are you adding or taking away from this number?
Yeah.
So this is the 6.6, but there's 11 zeros before that 6.
Okay.
This is 5.9, right? But there's 24 decimal places after that 5.
Okay.
So these are huge numbers.
Yeah. They do that so you don't have to write all that zeros out.
But we're doing everything in base units. So meters, kilograms. Okay. So far we have created G. Oh, actually, one thing that I want to do. Gravity is an object as well, and it contains G. Just to make my life simpler a bit later. And also to make a joke that I've just made gravity a thing. So guys, gravity is totally a thing. Okay. So next thing, we have R squared. Okay, so R is the distance between Earth and Moon. So we need some way to keep track of distance, and we need some way to keep track of position. So Earth and Moon will get their positions. and each will, and they'll be just entered as two coordinate system thing. Oh, where? Like this. I don't know if I need to go this basic, but let's do it anyway. So just whenever you have any object or object or position, you can enter it by saying how far it is on one axis and how far it is on an axis that's at the right angle to it. And those will be marking it as XY. And that will be useful for us because we're showing it on screen and need to calculate where we'll show these things on screen. So when we need to calculate the distance from this object to this object, we can calculate it by calculating this distance and this distance, right? The distance between these two lines and the distance between these two lines, right? And that's basically, so if we are the observer, you kind of know if you have two things, one thing is 5 meters away from you and the other thing is 3 meters away from you, you know that those two things are 2 meters apart. You just subtract those two numbers. And that's basically all that we'll be doing. So this will be the X, this will be the Y. We'll subtract their positions to get their X distance and Y distance, and then we'll just calculate the diagonal of that triangle. So it then becomes a right angle triangle. We can use Pythagorean theorem to solve it. So we have positions, and with that we can start calculating the force. So get force is a function which takes two parameters. Now, usually in programming, we'd be very generic about what's going in, but this will literally be Earth and Moon in our case. We won't be doing anything else. So a function is kind of a black box in programming where you list the things that you will put in it, and it will give you some value out. So in this case, it will return a force. Force, damn it, don't type what you're saying. So we need to calculate that force. To calculate that force, first we need to get a second. Oh, so yeah, this is where our formula goes. So let's do this. Define force, which is equal to gravity G, as defined here, right? We've already defined that, times Earth mass times moon mass divided by the distance. Okay, we need to calculate that R. There are definitely points that you can test your application, and we'll be doing those. So basically, all I'm doing is starting from the formula, defining everything that I need in that formula, and just kind of adding the stuff that the program needs to deal with it, right? I'm not really doing anything yet. I'm just translating it into a program. Let's say. We can definitely do some early simulations in console just to check what happens and what the function does, right? I don't have enough yet. So G, Earth mass, moon mass, and we need to calculate that distance. Okay, so let's calculate the distance. R, caps lock. R is, so we need the distance in X and in distance in, okay, so first we need to calculate Rx. So the distance on the X-axis, which is Earth, equals Earth position X, minus moon position X. So if I just subtract one from the other, I will get the distance on that axis, just as I just showed drawing. The distance on Y is position Y minus moon position Y. Again, if I just subtract the position of one to the other, I'll get their difference in position. And from that, I can calculate their overall distance through Pythagorean theorem, right? Pythagorean theorem, which states that the diagonal of a triangle is equal to the square root of the sum of the squares of the sides, right? And that's what we'll be using. So it's root of square of Rx plus square of Ry. Okay, so we need to define root and square. I'll just do that quickly. Function root of a number will return, and I'll just use the math library, of n function square of number will return, we can do n times n, so a number multiplied by itself is its square. And we'll get the distance between the objects here, and then we'll just do square r here. Okay, so this will give us the force in newtons. Why newtons? Because we've defined all the things in their SI units, so meters, kilograms. So automatically it will be newtons. What? No. The program doesn't correlate at all. The way those units are defined. So Newton as an SI unit, the unit of force, is defined in meters, kilograms, and seconds. Right? So if I define all the other units, if I only exclusively use meters, kilograms, and seconds, I will automatically get newtons in any force equation. Right? Those things, all of those units cancel out just the right way or add up just the right way. In the same way that if you're calculating speed, right? If you're moving at if you move 1 meter per 1 second, right? Your speed will be 1 meter per second, right? And that's the unit of speed. So those units are kind of defined by so that the whole is consistent. So we have that. Now, one thing that will be a bit of a problem for me is that I will also need to separate out force in the same way, because I'll be calculating its effect on the x-axis and the y-axis. Not, I cannot tell it to act that way on a screen, right? If all the coordinates. So I need to take that force that I've just calculated, kind of split and say how much of that force is applied this way, and how much of that force is applied this way. Right? And that's the same thing as this, but kind of in reverse. I want to get Rx and Ry for the force, for this force, in the same way that I got this distance from them. So what I'm going to do is kind of just to make my life simpler, I'm going to solve the whole triangle. Take this distance and get all the angles and all the sides and everything, and then use those to work from. And I might get back to that to elaborate a bit further, but let's do it like this. We'll make force an object. It's going to have 3 components: force X, force Y, and force R, which will be the diagonal one, the one that we calculated here. So force R is, we have calculated here. What have we here? We'll have to solve a triangle here. Solve triangle. Is, whoops. Triangle is solve triangle given its sides Rx and Ry. So, whoops. What I want to do is get an object that will have all the sides defined and all the angles defined. And for that, I'll create a function to solve the triangle. Function solve triangle that takes two sides of the triangle, two shorter sides of the triangle, right? So A and B. And then, and return, whoops, don't do that. Returns, returns a triangle. I'll define that triangle as an object. That object will have sides, and it'll have angles. The sides will be A, B, and C. And the angles will be defined as the opposite side of the triangle. So if we have a rectangular triangle, something like this. Oh, damn it. Give me these, make this thicker, right? So if this is a triangle, if I have side A, side B, side C, right? So this is standard nomenclature that the longest one is always C. What I'll be calling the angles is the angle opposite A will be called A. The angle opposite B will be called B. And the angle opposite, oops. And the angle opposite. Yeah, we'll fix it. It'll if something has been foobarred, it'll just throw an error and we'll figure it out. So once again, shorter sides are A and B, longest side is C. Angle opposite B will be called B, angle opposite A will be called A, and angle opposite C will always be a right angle. Okay, so that kind of helps us a bit. We'll call this A, B, C. That will be our triangle. So, triangle, side A. Well, that's already defined. We've passed it in, right? We have that in our incoming parameters. So it's just A. Triangle, side B. Same thing. Triangle, side C. Oh, that's our hypotenuse, right? It's this thing. So to make it a bit nicer, we'll just comment this out. We'll make another mathematical function. Function get news, which takes A and B as parameters and returns A and B. Is it clear what I've done here? Okay. So get hypotenuse of A and B. Right. Okay, how about the angles? Triangle, angle A. We can use it by getting what's it called? Let's solve the triangle. The Google way. Solve triangle. Nope. Solve triangle. Not sure why not. We're looking for a sine rule. Oh. Have it here. Why are there no? What kind of a math page doesn't have formulas? I need more formulas. Of triangle sine rule. What the hell? Right angle. Oh. Right. Yeah, this is what we need. So we have an angle, its opposing side, and the hypotenuse. The sinus of the angle is opposite sides above the hypotenuse. So sinus of the angle is opposite sides. Okay, so that's arc sine of A over C. A over O side C. And we'll be very verbose and put the same things here, just that it's clear what we're talking about. Angle B, same thing for B. And angle C is always the right angle, so that's pi half. So that'll return a triangle with 3 values for the length of the sides and 3 values for the angles of inside that triangle. And then back here, R is something that I've received back by solving the triangle. So triangle side C. Okay. Now we're talking. Force X. And now we need to do the same thing backwards. So we had the arcsine of the side and the hypotenuse, of the opposing side and the hypotenuse. Now we need to turn that back into from the angle that we got into a length of the force against the on the x-axis. So that will be sine of the angle, triangle A times triangle side C. This might be very unclear. Is it? Okay. So, what have we got so far? We have the Earth, it has a mass, it has a position. We have the Moon, it has a mass, it has a position. And we have a way to solve to get the force, which will give us the total force, the force, scalar force value overall, and it will also give us the force component of the force along the x-axis and the force component over the y-axis, and we'll just return it as one neat package.
All right. Let's just do the front. Perfect.
Okay. Oh, we didn't look up the positions. So for now, we'll have the Earth just dead center in our coordinate system.
Yeah.
And we'll just plot the distance of the Moon on one of the axes. So Moon distance. Oh yeah, right. And it will be by my distance. You have anything better? Orbit of the Moon. Perigee, apogee. There we go. So we'll be plotting it from the furthest point in the orbit. So we'll just put the Moon at 405, 400, and we're doing everything in base SI units. So those kilometers need to be turned into meters. So we'll just add three zeros on it. And that's the distance to the Moon in meters when it's farthest away. We have that. We are able to calculate our force of gravity. We can't do anything with that yet because we are missing ways to apply it. So the force will generate an acceleration, right? And that acceleration will modify the speed. So, well, let's do it this way. Which information do we need stored? To know what the next step in the animation will be, we need to know the previous one. That's sorted by position. But since we're dealing with accelerations, to change a previous speed, we need to keep track of what its current speed is, right? Mm-hmm. So we'll need speed, and we'll also be doing it along the X and Y axes. for the same reasons. And same for the moon. And for now, we'll say the Earth is stationary, and we'll put in the orbital speed for the moon. So, on orbital speed at apogee. Have it. There we go, orbit of the moon. So when it's farthest, it's going slowest. So it's 0.97 kilometers per second, or 970 meters per second. (970). 170 meters per second. Okay, so if it's this far from Earth, its orbital. If it's this far from Earth on y-axis, its orbital speed is perpendicular to that. So it's on the x-axis. Now we have speeds. What's next? We need acceleration. So what's the formula for acceleration? F equals ma, whoops, right? Or rather, A equals F through M. Know this formula?
Yes.
Okay, so we have the force and we have the mass of each of these objects. Mm-hmm. So we're going to need method get acceleration is a function that takes a force and an object and a mass. Right. And returns that's probably with one L less spelling. Yeah. And acceleration. Acceleration is force divided by mass, and that's all there is to it. And we now kind of have the bits and pieces to start putting it together. Function step will be a single set of calculations. What we need to do is get the force. Force is gravity. Get force between Earth and Moon. Next, we need to calculate acceleration. Acceleration against the oh, nah, we can modify the speed immediately. So Earth speed x gets modified by the x and Earth s. So now we're kind of connecting everything. This object's speed will get increased by the acceleration, which we calculate from the x component of the dimension and the mass of the Earth. On the y-axis, the speed will just use the y component of the force.
So at this point in the process, now you have all the steps the program needs to know what to do, right?
Yeah.
Okay. So I want to just kind of verify, because and is this the or I'll ask again, or let me know at what point are you almost verifying everything you've done? not when you put the model in, but like is there a step where you have to fact check through stuff, or not fact check, but check through everything again, or is that just as you go? Or as you
so so this function that I'm writing now is putting all of those things together to change these two objects, to change the speed by acceleration, then to change the position by speed, right?
Okay.
And when I do that, then we can run it in a browser and kind of bring up the console, call the function to run it once, to do all the calculations once, see what's changed, call it again, see what's changed, right? Mm-hmm. So we can kind of check it by doing numbers, by simply looking at how the numbers change.
So if, say, someone were to find enough data from some study that happened, and they put the numbers in themselves. I mean, knowingly they knew how to do this programming part or this scripting part, but they knew what data they were looking at. They would be able to fact check that data through these steps, or with this.
Yeah.
Okay. Because that seems, like I said, I was trying to. I want to figure this out because it's very difficult to do script for me, at least, and these kind of things are the projects I've been thinking about. I wanted to do to be able to present to people, how things work, and the first thing I thought of when you were talking about this was, well, they're going to go, well, he just enters whatever he wants in there and it just makes it go in a model. And I was thinking, no, you actually have to put the data that's been given to make it actually work the way, you're trying to, not this one, but, you're trying to present. And if they're not correct, you're going to know it.
So how does that work? When I run the simulation, I'll get a bunch of numbers. So I have these initial conditions that I've put in its distance, its orbital speed, its mass, right?
Yeah.
Everything that kind of has been given to me.
Yes.
And I run the application and get a set of numbers at certain time intervals. Let's say today at noon, tomorrow at noon, the day after at noon, and I will create an Excel spreadsheet output of or a database of these numbers.
Yeah.
At the same time, an experimental physicist or cosmologist, astronomer, whatever, will try to get the exact same data by observation, assuming the same model.
Yeah.
Right? So if the model is the same in both cases, we should be getting ideally exactly the same numbers.
Yeah. Okay.
Okay. Now, there are margins of error. Computers, especially especially normal computers, they will have kind of 7 significant digits, right? And then just literally won't care for the digits beyond that. So even though I've entered a 22-digit number here and a 24-digit number here, only the first 7 digits of that have any value, and the rest is just gibberish. Like it literally, it doesn't say, it doesn't connect. You can just replace it with zeros,
Yeah.
right? But it's replaced with zeros in binary, so it'll come up as some power of binary numbers. Right?
Yeah. Yeah. Okay. Yeah. It won't fit. Okay. I see what you're saying.
Yeah, but those things will still be off like 7 digits. 7 digits is a million, so we'll be off by 1 in a million, or so by a fraction in a million, right? 1 in a million will still be accurate. That'll be the 7th digit.
Okay. I see what you're, okay. I see what you're saying. So basically, it's when the data is finalized, then it's almost simplified when they're reading it or observing it. They know that it's the functions without without the extra.
So basically, when we'll be comparing information, we'll be comparing, let's say, just to simplify things extremely, we'll be comparing just the first 7 digits of each number.
Okay.
Because the digits after that are insignificant.
Yeah, no, I just caught on to what you were saying. I apologize. No, I get it now.
Right?
Yeah.
And if those 7 numbers agree, everything's fine.
Yeah.
Now, in practice, that's not quite that easy. So for me on a computer, that's very easy. I will know how much how much the accuracy of the data, how much memory I have allocated to each number, how many of those digits are significant, and I can just fix them. But for the person doing the observational measurements, his digits will also be fudged, right? When he measures that the moon has, I don't know, 1 degree radial width. Now, is that 1 degree precisely?
Sorry about that. Yeah, I'm sorry.
So how much aberration does the lens on his telescope put in, and how much was the ground shaking when he was measuring it, and right, what were the atmospheric conditions, was there distortion, stuff like that. So when he's measuring it, he kind of needs to keep track as much as possible of all of those things and define his error margins. Like literally say, this many digits I'm certain of.
Yeah.
Like there's no doubt. But then we get into kind of, well, this could be a little bit more or a little bit less because the image was shimmering. So when I put the ruler next to it, it was going between 1 and 1.1 degrees, let's say.
Yeah, that margin of error.
Right? And those are the margins of error.
Yeah.
So there are known margins of error and unknown margins of error. Unknown margins of error are things which are literally beyond his ability to measure. But then, like, I will know that he has two significant digits. Those two will be compared to what I'm doing. I will know that my result needs to fall between his error margins and predominantly needs to fall into the center distribution between his error margins. And so there will be some fuzziness in the data on each individual measurement. Now, if over a large number of measurements, we all stay within our error margins and our precision, then we'll call it good, right? It's that domain of imprecise facts. When I say that 1 + 1 is a number between 0 and 1,000, that's a fact.
Yeah.
But it's a very imprecise fact.
Yeah, exactly.
Right?
Yep.
I'm not wrong in saying that. I'm just not being very accurate.
Yes, I get it. Yeah.
So we're trying to get the accuracy as much, as narrow as possible, but still being sure to eliminate being wrong, right? And we'll only report the part that we know we're not wrong about. To that accuracy and no more. And that's kind of the whole secret of this notation is exactly that. It also informs you about how many significant digits you have.
Yeah.
And what.
Okay.
Right.
Yeah, so you're not exceeding it.
This has 4 significant digits.
Yeah.
And in his measurement, he will have. So as long as those align consistently and prolongedly, we'll call everything fine. Now, if my predictions keep falling outside of the error margins of his measurements, then there is a problem with one or the other.
Yeah.
That somebody is doing something wrong, and we need to figure out who. Another one is if there is a growing difference. Right? If we start off well, and for the first, 1,000 measurements we're good, but then slowly we start diverging and I get out of his error margins and then keep going farther and farther and farther and farther, then we can pretty surely say that there is something wrong with the formula. Okay,
yeah. And that's why it's always going, and they're always looking, and they're always, checking their facts over and over again. It's a never-ending story, basically.
And all of these, somebody was retesting Einstein's theory of gravity, is somebody has found a way to either theoretically calculate, right? They built a computer that can calculate many more significant digits, or somebody has figured out a way to more accurately measure something to more significant digits.
So that would be...
And then we'll run through this process again, but this time we won't be comparing the first 3 or the first 7, we'll be comparing the first 20.
Now, and if it's off topic, let me know. Is quantum those extra digits when they're talking quantum computers and all that?
Ooh, that's very off topic.
Okay, no, then ignore it. Just ignore it then. Because that, that would have been a question I had, and if it's not part of it, then I know it's not part of it.
Yeah. Okay. So it is, and so the thing that makes quantum physics so important and so mind-bending is that it doesn't align with anything. It doesn't align with logic. It doesn't align with math. It doesn't align with common observations, things that we see. However, the alignment between measurement and theoretical calculation is so stupendously in alignment. I think it's 30 or 40 digits. For comparison, 36 digits of pi is enough to calculate the radius of the observable universe to within a width of a helium nuclei.
Oh, okay, damn. Okay. Yeah.
Right? The significance of these digits grows really, really fast.
Yeah.
Right? Every time you add a digit, you have increased things tenfold.
Yeah.
Right? So, and I love the example Richard Feynman once said. So, quantum physics is like this guy climbing on top of Big Ben, taking a notebook and scribbling some maths on it, and then just by thinking and solving mathematical problems on paper, coming up with a number, the distance to, I don't know, the tip of the Chrysler Tower in New York. And then another guy going and measuring that with a micrometer and finding that the first guy was within half of a hair's distance, half of a hair's width of the exact number that was there. So it's like, and at that point you kind of have to go like, my intuition is worthless. My perception of reality in lieu of that kind of agreement just doesn't mean anything.
It's the same thing anymore.
Right. And at the same time, we still absolutely know that it's incomplete, that there are things missing and need to be added to it.
So then they're almost running those numbers over and over, waiting.
Yeah.
Yep. Okay.
So a lot of work in physics is just trying to coax out mistakes, trying to find the mistake at the 40-second point that is consistently there and that is outside of the error margins, so that we can say, yes, our formula finally doesn't work under some conditions, right?
So it's really is the situation of, or like I did myself, and a lot of philosophers, where they're constantly digging in that science is trying to prove things to us, when in reality science is always, it's literally looking to see an error in where what they've calculated.
There is no progress in science. Progress in science is impossible unless you can find a flaw. If you have a perfect solution, the one that works always for everything, that's the end of science. The science is done. Then all they have to do is bring it and say, we have solved it, give us our Nobel Prizes, and we're done, and there's nothing more to look at.
Everyone go home.
Everyone go home, right.
Sorry about throwing that off path.
That's fine. So yes, all of those scientists that say I have a finding which but on the other hand, there is a big problem of what if somebody just comes up and says, hey, I found the mistake in the third position, right? In the third significant digit is wrong. Okay, how did you find that? I'm not going to tell you.
I want the prize.
Yeah, it's my discovery, but it's wrong. Okay, fuck off, right? You're not contributing anything. You're just being contrarian to something. Like, if you don't tell us how, if we cannot confirm that mistake is there, like, if you find that mistake, that's very significant, immensely valuable, and we want it now. But that doesn't mean we'll just praise anybody who says there's a mistake, right? Because we need to know that we need to to be able to test that mistake and know that mistake and find something new on it. If it's not replicable, if your mistake doesn't show up for anybody else, then you haven't discovered anything.
I get it.
And also, right, in that imprecise fact, if I know that 1 + 1 is between a 0 and 1,000, then you coming up and saying, well, it's not 7, doesn't mean anything to me. And you coming up and saying it's not 7, and therefore it's 6 million. That especially doesn't help. Like, I know that it's not 6 million. Yeah. I know that it's greater. Like, I know what my error margins are.
Yeah, that's, you know, when something's seriously wrong at that point.
And a lot of both creationist and flat earth arguments fall into that category of, look, you say it's somewhere between 0 and 1,000 and it's not 7, right? I know that it's not 7, therefore it's 6 million. It's not 7, which is a number between 0 and 1,000. Therefore, your whole setup, it can be thrown away. I don't even have to consider you. I can just make up anything. Okay, let's get back to what we were doing. So, speed, we've modified to the existing speed, adding gravity on that axis. For the mass of Earth, same for the other axis same for both axes of Moon. Position, so again, just to be crystal clear about it, what is acceleration? Acceleration is change of speed over time. So whenever we do a calculation, that speed will be changing slightly. So we'll take the old speed and just modify it by the acceleration, right?
Yes.
What is speed? It is change of position over time. So we'll take the old position and just add to it speed, right? Right. And same thing for the moon. Right, and now we have a moving system.
Awesome.
On every tick of this step, the speed force will be calculated. The speed will be modified by the acceleration that we get from that force. The position will be modified by the speed we got before, and thus the position will change. Okay, let's, what?
I was just gonna say, I wanted to kind of, well, I guess it'd be almost the obvious, you know, answer, but it should be very clear that in order for you to create this model, you needed a lot of data, and to then get that data, you had to have made a lot of observations, and you know, and I think that a lot of flat earthers forget that part, in the sense that because you don't believe something doesn't work a certain way, you can't just say, no, it doesn't. It does not work that way, because there's all this data that didn't just come about yesterday, that's being used to explain where we live and explain the answers that are explain the questions that we have, and just saying, no, I think I figured out a new way because I just don't think it's a globe, isn't a true, honest method of it. In science, that I know you hate science, but it's very clear.
So if we're talking about science as in the human endeavor that's been going on for hundreds of years and what we know by now, no, you're not bringing any contribution to that. However, you can, what you are doing is the very first step of science. Like if you are trying to go it alone, say I will ignore all of human knowledge and just start from scratch, or I will pick and choose what I'm going to take. You just have to be very, very careful not to take things which discount you immediately, as in being contradictory to your thesis. And then it's kind of fine. You can have creationist science, and you can have flat Earth science in the sense of, I speculate that this is the case. In order for that speculation to become a hypothesis, I need to be able to make predictions that can be compared to observations. And that's what we're kind of doing here, right?
Yes.
That's the thing of where's your model, right? Where's your process for generating a set of data, right?
Exactly.
An Excel spreadsheet of data that once somebody goes out into the real world and looks at it and generates their own Excel spreadsheet of observations, that we can compare those two and say how well they align. Right? If you don't have that, you're not doing science.
I call that a mic drop. Boom. That's exactly how that's. You couldn't say it any better.
And you can do flat Earth science. It is perfectly valid. Like, a lot of people will disagree with you. They will think that you are doing a silly thing. But if you turn your speculation into hypothesis, right? If you make some sort of predictions, and then you transparently show what your predictions are and how they align with observation, you can get your hypothesis to be valid within your own scope of science. It will still not affect the overall science, because we've looked at those things. We measure things to 40 significant digits. You will not be able to measure it to 2 significant digits, but fair enough. People who had done these observations were at the same time machinists and optics and grinding their own lenses and looking for ways to eke out that one more digit. And contribution of famous people have become famous by eking out an additional significant digit, by decreasing the error margins by 1%. That can be a person's entire lifetime of dedication and devotion from the smartest people in the world.
So
if your idea is that you're going to sit down and just generate all of human science and technology by thinking really hard about what makes sense to you, you're not.
Yeah.
Even the smartest people, like there's 3 or 4 instances where people were able to do that, and even those people were building on the shoulders of giants of people who came before them.
So it's almost unheard of for a scientist to come up with something. It's the years of work that led him to get to that point where he found that anomaly.
So the most prominent single person discovery, or kind of that theoretical proposition, was Einstein, and that was one of the last ones who had the opportunity of doing it all alone. Right, of just taking a look at what exists and then coming up with a one-man solution that covers so many things so well.
Yeah. See.
We've fine-tuned our knowledge so well that at this point, like you do not have enough time in a lifetime to learn all of this stuff. You have to collaborate. That's another thing. When we're talking about comparing prediction to observation, there is a reason why physics are split into theoretical physics and experimental physics. It's not the same people doing them, right? It's not as valid if you are the one
Doing it all, yeah.
Coming up with the model and calculating the predictions from the model and collecting data, right? Why? Because not because people are dishonest. Well, because people are dishonest, but because people are very willing and able to delude themselves.
Yeah.
Right? Because if the margin is like, if you get 20 digits of agreement and then a disagreement on 21st digit, and you've been working on this your whole life, you might be willing to take that measurement again.
Yeah.
Just to make sure. And take it a couple of times, and then if you get one which coincides on the 21st, say, "Oh, look, I got it precisely." Right? And those are the things that kind of science as a process is trying to eliminate. Eliminate the biases, intentional or unintentional, desired or undesired. Right?
Yeah.
It has to work always for everybody.
Until it doesn't.
Until it doesn't. And then you get a lot of scientists excited by, oh, we're finally about to see something new. So let's do a first experiment. No, not that one. Gravity, I think. Is it? Unexpected. Curvature 71. Debugging. 71. This was what somebody was warning me against, I think. Oh, once again. Gravity 72. Oh, yeah, I see it. Yeah, this is a comma. Another one. Did I save it? I did. Okay, no more errors. So now we have our Earth, which is an object, right? We have our Moon, which is an object that has all these properties. And we can run our main function, which is called next step, which is called step. Function, if I execute that function, solve triangle is not. Solve triangle. Solve triangle. No, this is the one that he's been warning me about. Solve triangle. Right. And yes, the people who do these things also make typos. Cannot set property A of undefined. And then you just go through it and find all the errors and correct them. Triangle, of course. Triangle, sides, side, angles, angle. Oh, both need to be named the same. Step, triangle is not defined. 28. Triangle, opet. Triangle, 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 triangle. Typos, typos everywhere. So many typos. Step, arc. Oh, I did not define the arcsin. Okay. Function arcsin of n. Turn math basin of n. Also function sin of n. Return math sin of n. And the lovely thing about computers is they can do math, so you don't have to. You need to know what these things do and how to use them, but you don't have to know how to calculate them. Oh, that's where they get us. Is not defined. All right, C is indeed not defined. It's triangle. I can spell triangle in 20 different ways. Side C. And as long as all of your arrows are typos of that kind, yay! They're very easily resolved. Yeah. So, having run one step, the moon has moved along the x-axis by the amount of speed. Yay! Let's run a couple of more steps and see what happens to the moon. Oops. Okay, expand the moon. Oh, right. Expand the moon. So it's traveled 11 kilometers, and it has started gaining speed on the y-axis. We'll see what happens. Okay, so we'll create an output on the screen and run this as an animation. Actually, at this point, we might actually start already creating the display. G for it. Perfect. 1,000. We'll need a circle. Cx is something. Cy is something. We'll call it Earth. Oh, this C machine. What else do we need? We need a radius. Am I forgetting anything? Cool. Now we can just copy Earth and turn it into moon. Moon. We'll need to give them a fill so that we can see them. Earth will be some shade of blue. And yeah. And moon will be gray. We'll need a style sheet. Background color, make it black. Height up. This red. See. Let's see. Oh, nope. See some things. Right. Okay. Oops. View box. It's not viewport, it's view box. Right. Okay, better. I will not be explaining this part. This is just what design. This has nothing to do with what we're talking about. Up to left 0. We go. We need to control the scaling, which will be reserve aspect ratio. The ratio is x mid, y mid, split. Oh, slice. Slice. Whoops. cx cy 0 0. We said -4 minus 500. 100 minus 500, 1,000, 1,000. There we go, there's our Earth. Why is the moon not showing? Ratio. What the hell? I know what I'll do. I'll cheat. I'll cheat by going to the old version of application, just taking the page from there and therefore skipping the part of page making. There we go. Nice. Sweet. Is that the one? Okay, so this is the right interface. It just isn't connected in any way. Nope. This is fine. We need this one. Oh boy. But somewhat simpler. G-force, we won't be calculating that. We won't be using the controls yet. Hey. Okay. So now that we have that, we have Earth X, Earth Y, Moon X, Moon Y. So when we make a step, we'll just ID Earth X HTML equals Earth position X, Earth Y is Earth position Y. Do the same thing for the moon. Save. And now if I call the step on element, call step, yay, I get their coordinates. And now we can create an animation by calling request animation frame. Yeah. So this just executes the function every time my screen tries to show the page, which will be 60 times per second. And now we get motion. So this is the output that you were asking for. The first, okay. We'll also bind it to the objects themselves, which are called SVG Earth and SVG Moon. Get rid of these ones for now. SVG Earth and SVG Moon, and we'll be setting the center X and center Y properties. We can see what we're doing. SVG, SVG Earth. As I said, this part gets a bit boring.
Oh, no worries, no worries. That's me.
Set attribute CX to the value of Earth position X. CY, Earth position Y. Do the same for Moon. Moon. Moon is not Moon. Right, and the only thing that I need to do is that this has a scale to it, so I'll divide them by 1,000,000 just to make them fit on screen. Otherwise, we would be getting an animation in real. No. We would be getting. If I don't divide Earth position and Moon position by 1,000,000, I will get them at their appropriate sizes and distances. Right? They'll be on my screen. They will be 405,400,000 meters apart. That will not fit on my screen. Okay, inspect. Yeah, this is working. Now we have a real-time simulation of the exciting, right? A real-time simulation in proportion of the Earth-Moon system. Right? Yeah. So the way I divided that by that size by 1,000,000 for it to fit on screen, we're also going to need to do something to make it run at anything faster than real time. Because at this pace, it will take us 28 days for the moon to make a rotation around the planet. Well, actually, no. This is sped up. So this is running at 60 frames per second, and each frame is calculating as though the frame is a second. So this is actually running 60 times faster than real time. right? Exciting, blistering motion. Okay, so go ahead. Eclipses can be done in a whole bunch of different ways, but yes, you will need something like this. So yeah, but so the ancients did it by practically brute force. There's a system which keeps getting referenced in even in this channel, which is something beginning with S, but I don't remember what the right name was. Well, basically, the ancient way of predicting eclipses, which was just a matter of keeping observational data. Whenever an eclipse happens, you note the time and place, and you do it again, and you do it again, and you do it again, and then you start noticing patterns. Well, if it was here, then it will be here in 57 years and in another 57 years, and there's another cycle, which means that it will be here in 11 years, and there's up to 1,000 different cycles happening on at the same time and interfering with each other, but they will tell you when the eclipses will be. Just by brute force looking at when the sun has come up, when it has gone down, when the moon has come up, when the moon has gone down, and when the eclipse happened. That's a way of predicting the eclipses without any model and any calculation beyond pattern recognition. I need to Google it. Ellipses. I just need the name. Saros. Right. So Saros is just literally a pattern recognition method of predicting it. If you have enough time to keep accurate track, you will notice that some things happen with a regularity. Well,
yeah, but then okay, yeah. So yeah, because I'm thinking, our lifetime, but these are, the ancients. I mean, they had. I don't even know how much time, but I mean, I'm thinking too small when it comes to how they figured it out as well.
Look, take away illumination, take away entertainment, take away, like you're taking, if you strip away civilization from people, all they have to do, like all that's available for them to do is when the sun goes down, they can either immediately go to sleep or they can look at the stars. Right?
Yeah.
That's the thing that you can look at. The stars, the moon, the planets, right? Mm-hmm. And you can talk to each other and tell stories. And when your chores are done and when you're not doing anything, all that you have to do, all that's available for you to do is to sit down and look at the world around you. So people had lifetimes of time of no information beyond just looking at the nature and then telling their children about what they saw, so their children would, when they would look at the nature, would know, that's what grandpa was talking about, or right?
Yeah, and that's the insane part about it, because you a lot of people think, how easy is it just to look up and figure this out, and just like you were saying, we really have become accustomed to not even needing to look up. No one thinks to look up. I didn't look up. I didn't I gave a crap less about the stars and planets and stuff. That's why when came time to where do we live, I really didn't understand our solar system and just the dynamics of it. I think these are other reasons why flat Earth is a thing. Once you spend less time staring up and looking at the stars and your surrounding world, you trade it for conjuring up your reality rather than actually seeing the reality.
Yeah, and in between seeing eclipses, you have years and years and decades. Like I've seen the eclipse twice in my life where I live, and of spinning stories of what it was that you saw. First time you saw it with your ancestors didn't tell you about it, it was the most horrifying thing that ever happened because the sun got eaten by something for a while, right? And then you start spinning tales. What was it eaten by? Well, it was eaten by a giant wolf that chased it down, and we didn't see the wolf, but we saw the fight it was taking out of the sun.
Yeah,
right?
yeah.
I need to tell my children about it, and I need to tell, right?
Yeah,
So
I call
when
that
see it,
the phone call game. You, you tell a
yeah,
story and then pass it down, and eventually it becomes a completely different story.
and that's how you get a mythology, and that's why mythologies around the world are largely consistent with each other, because an exciting thing in Europe in the Stone Age was equally exciting in South America in Stone Age, right?
Mm.
Lightning, eclipses, earthquakes, right? And people would spin stories, and details would change, like, oh, it was a god, or it was a demon, or it was a wolf, or it was
Bigfoot.
Bigfoot, right? But they're still describing the same basic event. They're describing a flood, or they're describing a lightning strike, or they're describing an earthquake, or they're describing an eclipse. So you will have alignments between those stories. Where were we? Okay, so I've moved this. We need to make this go faster. Now, there are smart ways of doing it, and there are dumb ways of doing it, and we'll first do it in the dumbest possible way. That when we calculate acceleration, we'll just do it a bunch of times. And when we calculate speed, we'll just do it, we'll do it even dumber. We'll just multiply everything by 1,000. Oh, because I want to show you one of the mistakes that you'll get if you try to do this yourself. Why the algebraic method isn't good. Whoops. There we go. Whoa, it's not curving. I am missing something. Wait. Speed x, speed y, speed x, speed y, force x, force y, force x, force y. What is my force? Am I storing force anywhere? I'll store it in gravity. Force. Gravity will get a value for force because I need to see what's going on. Because we have an error. Our moon went away. Gravity didn't exist. That's true. gravity apply. Yeah. Force not defined, gravity 5, force not defined. Oh, right, gravity force. Good. Speed. Why is speed so tiny? What am I doing wrong? Moon position, moon speed y. Moon speed y, gravity, acceleration of force y. Force y with moon mass. Gravity force y. Acceleration. Mass. Okay, moon. Let's see this thing. This is tiny. Why is it so tiny? $22. Get hypotenuse of triangle. Get force, get acceleration. Force divided by mass. Let's just F equals MA, A equals M, that's fine. My mass is too big, my force is too small. My force is too small. Ooh, what's this? This is wrong. It's like this. It. It's not working. Okay, cheating time again, I guess. So this was similar. I have force calculations somewhere in here. Is it okay. Acceleration, force over mass, that's fine. Sin angle times hypotenuse. Do I have that? Sin angle A, C, okay. Opposite, force X is get opposite. Force D, force is square of distance. Whoa, 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 whoa. I have a typo somewhere. I have to have a typo somewhere. North position. Oh, I need to, yeah, I see. Here, I need to multiply everything by 1,000 if I'm going to multiply by 1,000. And these, I don't need to multiply by 1,000 at all. It's not working. Is it not working? What am I doing wrong? Own position Y is just tiny. AB, get hypotenuse, square A, square B root, that's fine. Arc sinus side A over side C. Get angle opposite over hypotenuse. Opposite over hypotenuse. Arcs in, yeah. I'm sorry if this is boring for the audience. No, I've done this before. So it, 'There is, for some reason, my acceleration in the y-axis is just tiny. And I can't for the life of me see why. Thousand. Okay, so one thing is that the acceleration on one body needs to be okay. Get acceleration, force over mass, okay. Force, triangle distance. Force the, ooh, is that it? Yes, I know where the mistake is. Because I've calculated the force from the distance. I've calculated the components of the force from the distance rather than from the total force, and that should make it better, hopefully. Yay! Yeah, if your force should be a 20-digit number, it really doesn't help if you just take a couple of digits. Yeah. So one thing is visualizations are actually done fairly rarely, and they're mostly done as a marketing stunt. Sometimes the scientists will do it just for the pleasure of doing it, for the pleasure of seeing the result. But in a lot of in a lot of cases, that doesn't add anything, especially if you're testing a known hypothesis, right? Yeah, they're in that data. So what you will have is a supercomputer doing a calculation which is way more complex than this, which is basically this, just using smarter math and a lot more complex calculations, in the sense that it will have millions of bodies or stuff like that. It will generate a spreadsheet of key data, or it will generate like petabytes and petabytes of outcome data that can then be analyzed, where you don't have to calculate them anymore. We have the data, now we can look for patterns. Okay, how many cycles per I don't know, period of time, or where will this thing be in 2,000 years, or right? When was the last time that these two things were aligned in such a way? Somebody says that they don't hear you.
Yeah, I'm fixed it. Trust me, guys. I'm not saying much. Wow. Yeah.
So it's more about generating the spreadsheets of data, and if you do this long enough, and if you deal with these things long enough, the stuff that I'm doing here, you can kind of do it in your head.
Yeah, like you were saying with right. The scientists and or I'm sorry, the entry of this.
Yeah, and you can do it in your head in such a way that you can actually look at a spreadsheet and kind of pick out this piece of data and this piece of data and this piece of data, and immediately extrapolate whether it's an object in orbit or whether it's elongated, or right, because you've been looking, if you're an astronomer, you've been looking at these coordinates all your life.
Yeah.
You know exactly what X and Y mean.
Yep. Okay, yeah, I see what you're saying. You've traveled that data path 100,000 times, studying it and looking at it, so you've seen that data point. You literally see it in your head. That's kind of how it works for the surveying to a point where you know your points. So when you're looking at a topo map, I can use a topo map just as good as I can use a road map. You know what I mean? So
yeah. So this extra step of making it visible is usually not done. When it's done for either kind of informative purposes, for demonstration, for marketing, for kind of
I call it selling.
Explaining to laymen.
Mm-hmm. I personally call it selling space. It sounds bad, but they want the future. They want the people that want to invest in a NASA, in a site, what do you call them? What do you call it? An institute that may be on to the next thing. You know what I mean? So they got to keep them wanting them to research things and want them to look into things, and but at the same time, like you were just saying, where they don't usually do this. Again, if NASA gave us only raw photos, you understand that 90% of us would have looked at a blob that's black and white and pixelated probably, and we would have thrown it away right away. I mean, sometimes, sometimes it's just not what you think it's going to be, and they have to make it visually pleasing to you to want to look at it, to want to know what the hell's going on.
Another thing is the data is in non-visual context. So let's say we take a picture of a star, and when you take that picture, the picture, if you just show what's in the picture, it's 4 pixels, right? 4 pixels are 4 bits of data. But when you look at what they recorded in that viewing of the star, it's gigabytes of data. So what's all that data? All that data is how the spectrum of the star has changed. What was the value of each frequency in the spectrum, right? How it changed over different recordings, over different amounts of time. So they will have all of this data that will correlate, which if you were just to visualize it, all you would get is 4 pixels minutely changing their frequency, and they have gigabytes of it. What are they doing? That data contains exact wavelengths of which elements are in which proportions in that star. How hot is it burning? How fast is it moving away or coming towards us over a period of time, over multiple observations, so that you can kind of say what's within the error margins and what are those like atmospheric aberrations or another object occluding it, or right. So the images and the visualizations often don't work. So one thing that's happening while we're talking in the simulation is that the simulation is slowly drifting aside. Right? Mm-hmm. The Earth is no longer at the center. You see that? Mm-hmm. So what's going on there is that I haven't been paying attention to the conservation of momentum.
Okay, so yeah.
Well, it's all working fine, except when I defined the movement, the initial state of the system, Earth has a position of 0 and the speed of 0 in both axes. Moon has a speed in one axis. That means that the whole system has a momentum, right? Moon has momentum in one direction, mm-hmm. Earth has no momentum, and there is an average there. Yes, that the whole system has a momentum, so we've kind of shoved the Earth sideways as well.
and so we need. How long would it take for this system to, what do you call it? Basically destroy itself or throw itself out of orbit? How long would that take?
It wouldn't.
Oh, okay. Is this so insignificant then? No. Look at it this way, right? Just general relativity, not Einstein's general relativity, just the concept of general relativity. Everything is relative. So either the whole system is moving slowly to the left, or you can also view it as the whole system is staying still, but our camera is slowly drifting to the right. Ah, okay, I see. So yeah, it's no matter what, it would just be it's a little bump to the side with everything. So it would play no difference.
Yeah, exactly. So what we can do is we can put the real center of that system, calculate the real center of that system, and put that at the center mark instead of putting Earth, because Earth is not the center of the Earth-Moon system. It's not even the Earth-Moon system is geocentric, right?
Yeah, it's not. Yeah.
At the same time, the moon is orbiting around Earth. Earth is also orbiting around the moon. So they both end up orbiting around a point.
Ah, okay.
Right?
Yeah. So, yeah. So
equilibrium.
We perceive that we're going around the sun, but okay. Yeah. Everything else is still going.
The same. So, the force, and you've seen it in the calculations that I've done. The force that's acting on the moon, that's kind of changing the moon's path.
Mm-hmm. The 2 years, 2 centimeters away.
That exact same force is acting on Earth in the opposite direction.
Yeah, it's like when you grab someone's arms and you twist, and you both do that. You guys both spin.
Yeah, exactly. It's just that the Earth is so much more massive.
Yeah, it's gonna have
that it moves a little bit, and the moon is so much smaller that it moves a lot.
Yeah. So what we're for that orbit we were watching. Obviously, you can speed it up to whatever you want, but how? I mean, are there models still going like that? Will they'll just run forever, or a programmer's going to run forever? Do they do that?
Okay, so I'm doing a very outdated model. So this is a Newtonian model, and even Newton would kind of laugh at me for doing this.
No, but this is the basics of figuring out.
I'll explain.
Okay.
When Newton was solving this, he did come up with the formula that I just wrote the algebraic solution to, right? I calculate every time that I can calculate, I calculate where it's going to be on the next spot in one step. What Newton noticed is, and like it's kind of obvious, right? If I've sped it up by moving it 10 times that, right? So if I calculate, let me just, I know how to stop it. No, I need it in stopped state, so I'll do this. I will not start it. Did I save it? Push. What the hell? Is it not low? Am I editing the right file? Graph.js, yes. I just need to clear my cache. Okay, here we go. And I really do want to in the moon and position. I haven't written that part. Never mind. What I was going to say was, so I'm at this position, right? And I calculate the force over the next 1 second. And it's going to give me a position here. That's fine. But if I calculate the position in 1 hour, right? Mm-hmm. I will get a much bigger force, a much bigger shift in position, and it's going to end up about here, let's say. Right?
Yeah.
And if so, the orbit of the moon around the Earth is 28 days. What happens if I tell it to calculate in one step the 28 days? It'll calculate the right distance to pass, but it'll just move it completely way off screen, far from Earth, right? So there is an error, right?
Yeah. Okay.
There is an error accumulating in each step that we do. And Newton was kind of struggling with that because he wanted to calculate. He didn't want to do this. He didn't have a computer. He couldn't. Yeah. He couldn't do calculations like, okay, do 6 million calculations to find out what it's going to do in the next 2 minutes. He wanted to find out what it's going to do in 2 months, right?
Yeah, yeah.
So what he noticed was, like, if he did it in one step, he would have an error. But if he did it in 2 steps, he would have less of an error. If he did it in 3 steps, he would have even less of an error. And there is a relationship between the first one that he did, and the second one that he did, and the third one that he did. And he found a way of taking those like couple of first calculations, and from them extrapolating precisely what would it be if he calculated infinitely many steps.
Oh, right? Shit.
Instead of calculating infinitely many steps, he found a way of calculating, of extrapolating from several degrees of calculation what would be the most precise outcome. And what he did there basically became calculus. That's why people say he invented calculus. That is calculus, right?
I get it now.
So, with my way of calculating things, with the algebraic solution to the formula, if you did 28 days of animation, you would have it jump just way outside of the... But if you did it with calculus, it would do a perfect circle in one calculation, right? You could say, where is it going to be in, I don't know, 6,000 years? And in one step, in one calculation, it will just do all the loop-de-loops and stop at the position where it's supposed to go, right?
Yep.
That's why calculus is so powerful.
Everything's about simplifying. But damn, making it harder. Fuck. Because calculus, man.
And so, but think about this. Newton had the foresight to notice this problem without a computer. Another problem that he noticed. Let's do this. I'm going to cut cut moon's speed in half. Oops. Let's say like this. And run the animation. So its orbital speed is half, so it just doesn't go that far. It goes much closer and gets closer into the sun, right? This is also LEB. The conversation that we were having, here's the example of what we're talking about, right? The force is constantly acting on the body. It's bringing it in faster. It gives it momentum and then flings it around. And then that same force is slowing it down until it gets to the farthest point where it stops moving away from Earth. And then it starts speeding it up back to... Gravity never turns on and off, right? So it's constantly acting and causing this motion. However, what I wanted to demonstrate was we'll just speed the animation up a bit more. Will this be too much? Let's see. Whoa. Oh, is this what's happening to your animation? You said, and everything flew apart. Yeah. So one part is you were making your calculations in too large in steps that were too large.
Yeah.
Right?
Yes. That's why I got what you got on the first laps, and then it shoot off.
Yeah. Also, you need to be kind of careful of infinities if one object comes too close to the other object. Like if it goes into the center of it, it will just gain ridiculous accelerations. Right?
Yeah, that's what I noticed.
And that's what happens. That's what happens with black holes.
Okay. Okay.
And since you don't have the rest of the physics of black holes, of losing energy through gravitational waves and writing the appropriate manifold to do that, then what will happen is that your object will just gain infinite speed. Or
we'll put it this way. What's happening is I'm setting myself up to start doing some observations, and I'm going to find a slingshot system, and I'm going to get a Nobel Prize for finding and explaining how a slingshot system works, because I have a model for it. I make one every time.
Okay, so the thing that I wanted to show you with this, if I just let me run it again before it goes off screen. So with this eccentric animation, you can kind of see that it's changed. The orbit itself is changing direction, right?
Okay, yeah.
It was up down, and now it's almost left right.
Yeah.
Okay, so that's called the precession, right? That's a precession of an orbit.
Okay. That change. The change is the okay.
Yeah, the change of the angle of the axis of the orbit, right? It's almost as if the axis is slowly spinning. Now, Newton noticed this as well, and it was a problem because real world objects don't do that. All except one.
Well, that one that did that around the sun, right?
Yeah. So all of the other planets don't precess in that way. So this is another artifact of that error of calculation, of just making each step too long and kind of getting the object farther along the path than it should be by not calculating infinitely many steps in between, right?
Oh, okay.
So when you speed up your animation, in the top part, it's more accurate when it's moving slower.
Okay.
And in the bottom part, as it's moving faster, it accrues more of an error. So it goes off in a wrong direction.
Yeah.
Then it's fine, and then goes off in a wrong direction. It's fine,
okay.
And that's how you accrue that.
Yeah, because it's bringing it back. It's trying to bring it back into that orbit. When it slows down, as it's slowing down, it's trying to get back into an orbit, but
when it's moving slower, you have more calculations for shorter distances, and the errors don't accrue that much. When you're in the fast part of the orbit, the error accrues much faster because you have, right, this sudden jerk of covering a lot of space.
Yeah, the
and every error that you have in each step multiplies a lot. So it creates a precession. So how can you correct for that? Well, the right way is don't use algebraic solutions. Don't use algebra for calculating stuff like this. Learn calculus and use calculus, right?
In theory.
In theory, but we live in a wonderful age of computers.
Yes.
And so instead of doing this applying the acceleration 1,000 times and applying this the speed to the position 1,000 times or 10,000 times, what I can do, because my computer will let me, is do a for loop and actually calculate the whole thing 1,000 times for each step and then show it once.
Oh, damn.
Okay. So that error will still be there and it will accumulate, but this way it'll be way, way, way more insignificant and it won't be speed dependent. So it will affect everything equally. It won't affect the bottom of the curve more than it does the top.
Oh, okay. Oh, it will be calculated to work basically, rather than missteps or like you were saying, when it goes fast, it won't miss those steps.
Yeah. So in every step, we will calculate the force, calculate the acceleration and edit, calculate the speed and edit, calculate the position, right? Mm-hmm. And then we'll calculate the force at that new position. And calculate the force at the next position, and the next position, and the next position, and get a much, much more precise. So this is kind of throwing processing power at the problem instead of being smart.
Seems smart to me.
Okay. And now it'll just remain on this axis, this up-down axis, even though it's been accelerated by the same amount as the previous animation, right? Mm. And yeah, your computer can handle that fine.
And I noticed that now the way it's orbiting, it's actually lurching the Earth.
Yep, and it's lurching the Earth in the wrong direction because...
Well, what direction should it go?
It should go the opposite direction from the moon.
Almost like it should push it.
Yeah,
or Eminem has a full line of chainsaws. Yeah. Eminem.
Right. This is where I fucked up. So the Earth and the Moon have gravity affecting them in opposite directions. I have them affecting it in the right direction, in the same direction, right? If the Earth is pulling the Moon in the plus direction, then the Moon is pulling the Earth in the minus direction. They're being pulled together. They're not both being pulled in the same direction.
Okay. Yeah, you would. I see. I'll see.
There. That's the way it should be.
Okay, I see.
Okay. And another thing that I wanted to do was eliminate that drift. So we can eliminate that drift by finding the, what's it called? The barycenter. So center. Oh, I want to have the moon moving at its normal speed. And barycenter is a function. So there is a point around which both the Earth and Moon are going around, which is at their mutual center of gravity, right? Earth has a center of its gravity, and the Moon has a center of its gravity, and the average of those is the center of the gravity of the system, right?
Oh, okay. I see what you're saying.
So if I move that center screen and then calculate the movement of, like, instead of just giving the moon a speed in one direction, I also give the Earth movement in the opposite direction proportional to its mass.
Okay. So
then they will just stay spinning in one spot.
okay, I see what it is.
Right?
Yeah, I see. Yeah, okay, that is the issue that I have. That is the major issue, basically.
That's what we were talking a little while ago when I gave the moon a mass and a speed in one direction. I have given it some momentum.
Yeah.
And Earth has a mass and a no speed. That means that the whole system has some momentum in that direction, right?
Yeah.
So we can negate that by making the Earth have an initial speed in the opposite direction to cancel it out.
Okay, I see.
Okay, so for that,
It's almost like you have to figure out a way to make the computer understand.
Oh, so the computer just does what you tell it to, and it's doing everything that you're seeing is okay. It's correct, right? There's no problem with that, except that your camera is drifting aside.
Yeah.
As we've talked, right?
Yes.
So all I'm going to do with this is fix the camera to either move with it if it's moving, or with the system if it's moving, or basically to have it stay put, to have it stay put relative to the system.
Okay. Yeah. Again, I get it now. I have it drawn down. I'm happy. I get it. I see. And I didn't even think about that factor at all when it comes to, entering the data or even knowing what the hell you're looking at. The fact that you have to take in accordance to which also makes sense to why no one scientist can just figure it all out. Makes sense.
Look, you have two objects which are in a frictionless void. They'll be moving. If you don't,
they will.
If you don't set things up in perfect balance, they will just go away.
Yeah, I know.
Okay. So we have a ratio between the moon's mass and the Earth mass. We'll move. So since we have defined the variables for the Earth and Moon so that they're along the y-axis, right? Mm-hmm. We'll just slide it along the y-axis. So Earth position x. Do I have? I need their distance along that x. No, not x, y. I need their distance. Distance is Earth. No. Earth position y minus moon position y, and we'll just shove them both by d times ratio. Whoops. Moon. So that will center everything on the barycenter. And also, Earth speed, whoops, on the x direction is -1 moon speed x times this times ratio. So what this line does, if they're aligned on the y-axis, right, and the moon has momentum in the x-axis, then Earth needs to get some momentum in the x-axis on the opposite, in the opposite direction, so that the whole system stays balanced and has a momentum of 0. How much? So negative direction, the opposite direction of the moon speed, times the ratio of their masses. And that should get the system to not get off screen. Whoops, did that, oh, something wrong with my refresh. Oh, and it would really help if I didn't only define how to do it, but I actually did it. It's barycenter. Undefined. Oh, all right, and I need to fix barycenter after I define the objects. If the objects don't yet exist, then there is nothing to fix. Split. Yay! And we're not drifting anywhere. So there is also some stage fright involved here, where I'm trying to like, I'm very conscious of every long silence that I make and stuff like that. And right, I'm doing this live, people are watching, this is boring as hell, I need to do it faster, and that's how mistakes are made, right?
Yeah, so I personally assumed when I was a flat earther that these simulations that you created were easy to make. I saw them all the time. I was like, that's not very scientific, but at the same time, I didn't realize that it took all the data of all the time they've had data to, in constantly collecting data that enters into it. I mean, it's not just let's go sit at the computer and make a model. Because I mean, what you did, and correct me if I'm wrong, but what you did is nothing compared to actually creating a simulation of the solar system.
Yeah, it's literally nothing. Like what I've done here cannot be expanded to the solar system. So this is the Newtonian model.
Uh-huh.
It's the one that could solve for 2 bodies, but couldn't solve for 3.
Okay, that's what I think. Okay,
At that, even that Newtonian system was better because Newton was using calculus, and I'm just using the algebraic solution.
Yeah. Well, that was also because of the stream itself. For people like myself who would have zero clue what you're talking about. But
and a lot more opportunity to get lost in kind of making silly mistakes that you don't know what's going on. So what I've done here is just manually zoomed in, and you can see the Earth orbiting the moon.
Yeah, that's okay. It seems
Right?
it's awkward that you say that, but I get it.
So there is a point somewhere right about where my cursor is. I don't know if you can see my mouse.
I can. They can see your cursor on the screen as well.
Okay. So that point is within the Earth's surface, and it's about 1,000 kilometers below the surface. And the Earth is wobbling around that point as it orbits the moon, literally.
Wow.
Right. Or another way of looking at it, and kind of the way that we call these systems is barycentric systems, right? There is a barycenter, a fixed point, which is the average point of mass of the whole system that both of those bodies are orbiting according to their mass.
So then obviously we have that same wobble, or that same orbit.
Yes, we do.
And that is why we will also become tidal locked at millions of years down the road, or something.
So no, system wobble has nothing to do with rotation.
Okay.
Right.
Okay.
Earth is entirely free. I know that this visual kind of suggests that Earth is also rotating around that point, but it's not. Rotation is completely independent. So it takes the moon 28 days to go around the Earth. The Earth is rotating in that same direction, but way, way, way faster.
Oh, okay, I see.
Right?
Yeah.
So it's doing one revolution every 24 hours instead of every 28 days.
So it
However,
almost counters that. So we're not doing that exactly. Is that what you mean?
we are doing that, except that we're also spinning 28 times faster around our central axis.
Okay. Yeah.
While wobbling.
Yeah. So we're in super duper, can't even calculate it, slow motion right now.
What was I going to? Oh yeah. So you mentioned tides.
Yes.
So a part of the effect that the Earth is spinning in the same direction that the Moon is orbiting it, and the fact that it has a liquid surface or a fluid surface, is what's causing the Moon to slowly drift away. So in the direction where the Moon is, there is a tide, right? The Earth is elongated in that direction.
You got like a little booby.
Yeah, but it's also spinning faster than the Earth is rotating it. So the bulges that it creates are always pulled ahead by the frictions with the surface, right? If there is a bulge and there is the Earth beneath that bulge of water and air, because tide also affects air, right? Earth is spinning beneath that and kind of causing, by friction, spinning it up faster and causing the bulge to always be a bit ahead.
So the bulge leads the tide, or leads the pull, basically.
Yeah, the position of the moon, exactly. And the closer part of that bulge will affect the moon more than the farther part, because gravity drops off with distance. So what will be happening is that the Earth will be losing speed due to friction with that bulge, but the moon will be gaining that much more orbital velocity. Okay. Because it seems like the mass of the Earth is always just slightly ahead of where it is because of that bulge leading it. Right?
Yeah.
So it'll be falling not to the center of the Earth, but slightly ahead of it, meaning that it will constantly be gaining speed.
Yeah.
And the amount of energy lost by the Earth's rotation in friction and the amount of energy gained by the moon in that being pulled by the tidal force are equivalent. So. And as the Earth is slowly slowing down, it's transferring its energy to Moon's orbital speed. Moon's orbital speed means that it goes higher in the orbit and higher in the orbit and higher in the orbit, slowly drifting away.
Okay. Now, okay, damn. So it's not that the moon is moving away, it's that the Earth is kind of giving it a little nudge as it goes around.
Yeah, and that nudge is coming from Earth's rotation, which is then slowing down and the day becoming slightly longer all the time as the moon is.
But I think it's like what? I think it's like 3,000. I don't even remember the number. I saw it the other day though. I was looking at the dynamics of it, the atomic clock and all that stuff. Believe it or not, I had never even fucking heard of that. Makes sense though. Because I know someone was talking about digital, something about, they were ranting about how we used to be on digital time. It didn't make sense to me. And then I looked it up and it makes sense because I've run heavy equipment and all our engines run on tenths basically.
So yeah, I would say that we're about done with the basic application of this. We can switch to this more developed version a little bit if you're.
I'm interested. I'm interested, but we should break it up because I honestly I'm definitely interested in it. But if I get too much, I'll lose what we did earlier, and I don't want to do that. But we're gonna do it again. We got to do it again because it would just be like we're adding more steps. It'd be great.
Yeah, sure.
Now I got a question because not very many people get to see or even know what's going on right now, but in the background on the server, Chris has been messaging me, and he doesn't have very nice things to say about our simulation, and just the fact that how a simulation is created to him doesn't make sense. And I did offer him, the opportunity to bring his data, and you could enter it into this, into the computer. I mean, I don't know what it will. I mean, damn, I don't know what it could possibly ever do, but that's what needs to be done. Like, again, I didn't have a very great idea of what this was before Bernie even, presented it and everything. But there's one thing I did get the second I looked into this. What he has presented to us are these steps that a flat earther has to do after all the observations and data collecting. And then I'm assuming, you don't want to really do this either until you have enough data, right?
Well, so you can start off like you can make one observation and then speculate on what that means. That's fine.
Yeah.
If you're doing that, you're still in the kind of in the domain of science.
You would do that so that once that scenario or that variable happens, you're kind of ready for it, or so like you were saying, where it was you need the data, you wouldn't do it with only so little data, and then you were saying that they would extrapolate on that. I guess I'm not really sure. Maybe I just worded the crap out of that question, which I do normally.
No. So again, in the domain of imprecise facts, right? If they can make a very imprecise observation and then make a very imprecise speculation on it, that's a start. That is a valid start. That's not a problem, right? It will be a problem if you try applying with that to an astrophysicist, right?
Yeah.
But we're talking about creating a model from scratch without relying on the scientific consensus, right?
Yes.
Okay, make an observation, make a measurement, try to make it as good as you can, like sincerely and unbiasedly, and then try to speculate on what the consequences of that would be. What are the things that you can predict from your explanation of that thing? Things that you haven't measured yet, right? What I've seen these 2 points. I expect that there is a third data point there that would look like this. What would the next step that you have not yet seen look like, right? Mm-hmm. And when you have that, you have a prediction. If it's a prediction that's as rough as 1 in a million, it's fine, right? Yeah. But then it has to coincide with your observation for that 1 in a million. Yeah. Right? If it's 1 in 3, it's 1 in 3, but it has to coincide in 1 in 3.
Which
as accurately as you predict and as accurately as you can measure, those things have to coincide.
And that right there is where a flat earther says we need time. And yes, I agree. Especially after this, the scientific method and in the process to getting to a accurate prediction, right? I mean,
look, agreed. You need time, right? You need time to prove your speculation. The first question is, what is your speculation? What is your model? What is your idea how it should work? It doesn't have to be a correct one. I'm not asking you to give me reality. I want you to give me your speculation, and I'll tell you what's wrong with it.
Now, I have a question.
It would be better if you saw what's wrong with it yourself, but you give it to me, I'll show you what's wrong with it, and then you go back to the drawing board and fix it. And then come back and say, look, I found the solution which overcomes the problem that you've given me last time. Right?
Yeah.
And that critique, that thing that people are always attacking you about, no, that's not how it works, or no, look, when we measure, when we measure the sun going across the sky, we always measure it moving at 15 degrees an hour, right? Give me some model for that.
Yeah.
Okay, I can get it to move to vary between, I don't know, 10 degrees and 20 degrees. So it's accurate to some degree, my model is, right?
Mm-hmm. So,
Let's find where it's wrong. If it's wrong there, then you can try to fix it. If you can't fix it, if it never gets more accurate, if it never resolves the issues that are found with it, then it's just wrong. And people in physics and people in science constantly have to deal with that. There are 6 different competing models of gravity that we have. There are at least 12 different interpretations of quantum physics that we have. Only one can be correct. All of the other ones, those are all currently active fields of scientific research. Those are all still valid. But 5 of those 6, or even 6 of those 6, will have to admit that they're wrong. Right?
And we go with the theory that is the furthest along, correct? That's kind of how it works, or further along in the process of
it's so there's a lot of pragmatism involved there. Like, it doesn't matter if it's furthest along if it doesn't get you any further. If you're like, we go like the standard model of quantum physics is the furthest along that we've gone, and it is somewhat an area of research, but it's not nearly a hot area of the research as most of these other like modifications of the standard model. Why? Because everything that can be known about the standard model we have already extrapolated, and it works, and we're now fine-tuning the 40th decimal place, right? And kind of
okay, and that's
but
why
there's nothing.
And that's why if
there's nothing to be gained there, and the thing is, we're not getting anything in return for working there. So the thing that's most useful to you is the thing that will get you further, that will make you make better predictions. Regardless of how popular it is, that's the thing where a lot of people say, well, the scientific community is propagating this consensus and just kind of imposing it on everybody else. Fuck no. You can use whatever the fuck you want.
Until it doesn't
You
work.
can come up with a completely new physics, which is completely in opposition to the existing model, as long as it gives better results.
Yep.
As long as other people can use it, right? If they can use your model to get better results. If that happens, the old consensus will be dropped like a brick. Right? And everybody will be cheering, and like there will be a huge celebration over the fact that we have just dropped the consensus that we have defended for. But again, that doesn't happen just because somebody says that they have overturned it. It has to be useful. So in quantum physics, there was a big unsolvable problem of these multiple infinities showing up when you calculate interactions between small particles, like infinities all over the place that you just can't resolve. Some of the smartest people who were creators of quantum physics, they all got together for a conference, and there was a student. He was still a student then, like post-grad, but still a student, right? Richard Feynman, who came in front of the biggest names in physics and said, well, I can't do it with pure just numbers, with calculations, but you see, if I draw this squiggly line here, and this squiggly line here, and this line here, and draw all the possible combinations of squiggly lines and lines, literal graphical, and then circle every intersection in all of them, and for each of those do this calculation, I get the exact right result that I need to get. He was laughed off, partially. There, a lot of people were up in arms to such a way of solving it. And 2 years later, he was one of the most famous physicists, and everybody was using his method. And those squiggly lines are known as Feynman diagrams because that's Richard Feynman, one of the most famous physicists who has solved the biggest problem in quantum physics: how to get rid of the infinities and get actual calculations. And nobody doing something, literally drawing squiggly lines, but it had meaning, it had value, it had merit. It doesn't matter if they laugh at you, if you can get the better result. If you can get the better result, then the companies will buy your product, then the people who need to, same thing with numbers, right? We've been using Roman numerals in the West for thousands of years, right? And then the Arabic numerals and the concept of zero came, and it was considered vulgar. It was considered ungodly to take something from the Muslims, right? But the people who were doing the job, the calculators of the time, the scribes who would do your taxes and calculate your transactions, so they were forced by law to use Roman numerals, and they did it by doing under the desk all the calculations in Arabic numerals and in decimal system, and then just taking the result and translating it into Roman numerals. Why? Because that new system, as ugly and as unwanted and as forbidden by the system as it was efficient. It was useful. It was much easier to do things that way. And people will always jump to what's faster and what's easier and what's right.
Yep. All right, sir.
You can't stop the right thing.
I'm starving. I'm gonna eat. I did promise everyone this. I'm gonna come back on because I know. Put it this way, guys. If you did not take this as wonderful information, too bad. It's your problem. Because I'm not going to lie to you guys. I had an underlying reason for doing this. My underlying reason for doing this was also the fact that I have been begging for flat Earth evidence and answers. And right when I realized that it's not flat, I realized the first thing that I realized why it's not flat was because any observation that I made, even if, because I did make observations that did point towards a flat Earth, but I didn't know why, and I sure as hell didn't know why it didn't work with anything else that came along with it. And this is it, because I had data that was couple pieces from that side, a couple pieces over there, and you can't just throw shit together that it's not going to be able to make sense. And that's what flat Earth is. It's your nitpicking data, again, that's brought to you via the globe, and you're saying that things like optics are the reason for why we believe there to be a curve, and rather than realizing that at the very best, like you were saying, you can add upon something. You can make your view have value if it's of value to science, to people, to whatever you're trying to say isn't as is. You know,
if
no, go ahead.
If the exchange and the conversation was sincere, I would gladly sit down with any of you and help you improve your model. Like the $100 question the other night. Mm-hmm. I believe that I have an answer for it. I believe that I can model through partial refraction the right kind of atmospheric lensing that would produce that image.
I would
don't think that it would work for a video, but that would be a freak occurrence. Like it would have to be this type of hot air here and cold air here, and then 100 kilometers later inversion, and then 100 kilometers later another inversion, or 10 kilometers later another inversion. Like you would need to get some really freaky optics to get that effect through refraction. Yeah, that would be a local effect that would happen never and would be visible only to one observer standing at the right location. Yep. Right? So you would get one photo of that ever by the luckiest man in the world, and never again. The fact that there are video, like that video is perfectly consistent and lasts, and that observation has been repeated again and again and again and again, that tells me that solution doesn't work. Like I can solve the problem, but I cannot model it. Exactly. I cannot make it persistent and consistent with observation after observation. And I can explain one data point, but not all of them.
Exactly, and that's right. And that is the biggest issue. Like I said, guys, what happened yesterday didn't stop there. The pretty much the second that into the live stream, I went and asked that same question to Riley. I went to his on the server and asked him the same question. He was pretty quick to want to answer the question, and again, with all the confidence in the world, he even stated he made claims. The issue I don't think he was ready for was the fact that I didn't come at him like you're wrong, I'm right. I literally challenged him basically to a how do you get to an answer challenge. I noticed right away he spouts out answers. If you guys don't believe me, Riley's live stream today, I think it's about 20 minutes long, and Ranty's live stream are 100% all about my question to Riley. And between the two of them, for the observation we saw yesterday, I wouldn't do that to you guys. I'm not gonna play it today. Tomorrow though. They came up with something called it's called a Bohr tide. And because I've been talking with a lot of these smart guys, the first thing that I always think, even when I'm looking into something myself, is you need as many observations of that to basically come to a conclusion. And when you look into someone's claim, that's the first thing you need to look into that claim about. A Bohr tide is very rare. It's considered a phenomenon. There are only select bays and mainly river mouths that this happens at. It is kind of like a flat. If I were to explain it to someone who couldn't see it because it's not anywhere near you, it's like a Colorado River flash flood at the mouth of a river or in a bay. The observation we saw had nothing even close to what a tidal bore is. I suggest everyone go look it up, and then you can see how completely impossible it would be for what we observed yesterday to be because of that. He also incited riptides. Well, anybody who was a junior lifeguard, like myself, you know right away that a riptide does not occur on the surface of the water. And regardless, it's a drawback, and that... Man, if I ever saw a riptide like that, because you understand that if it was a riptide, that big tanker ship that was only showing the top third maybe, that thing would be in a whirlpool that would never let go. It's ocean, bays don't work that way at all. The other claim that he had made is that there's a visible piece of land It's called Slipper Island or something like that. And the problem was that I saw, was he decided in his live stream, he says it himself, I don't know exactly where the observation was made, so we'll just pick a spot. Well, I found 3 different spots with the description in Danza, the cameraman's observations. And I did the neurological thing. I fucking emailed fucking Danza. Hey man, can I get some information, some stats? I actually saw him in the chat. He was talking, one of the upload chats, he was talking to Roy. I mean, I didn't even realize that Riley and Ranty have been trying to push that observation we made yesterday as flat Earth evidence because of that island. Yet they don't know where he took that observation from. I took numbers from all 3 spots, and I can tell you right now, 2 of the spots, you can't see that island. And one of the biggest issues is, I don't even think Riley knew which direction he was looking in, because he named islands that you'll see in that video, but they weren't even the correct islands. Like, he didn't take into account, they call it, I've always known them as shade islands, where they're not actual islands. They're just islands that are just under the water. Well, I think he may have counted a couple of those. I don't know. I think he may have, I don't even know how he got to, to see what he saw. Like I said, guys, I'm going to do this again. I'm going to go live again tonight, and I'm going to get into it. I'll have a panel open. We can get into it. I would really like for Riley, Ranty, or Chris. I think it's kind of late for, I don't think Riley and them are up. I think it's midnight or something, way past that. But I'd like Chris to come back, because Chris has got, actually, I'm pretty sure everyone noticed, he's got this like weird boost of confidence. Like, he's finally found evidence that keeps pushing him to telling us how wrong we are. And I'm not sure if anyone's noticed, but like, he's actually going backwards. And I know why. I got an opportunity I went over to Nathan's, and Chris sits there and just listens. And who is he listening to but Quantum Eraser? Quantum Eraser made an observation for himself. I'm not sure if a lot of people heard about it or not, but basically Quantum Eraser debunked soundly. It sounds crazy, right? No. He debunked soundly. It was crazy. But here's the thing. I'm not going to even show you guys the footage until I come back in about 45 minutes. So 45 minutes, you're going to see, unfortunately, Quantum Eraser debunk Soundly Pontchartrain. I've already shown the footage to Soundly. He's seen it. He's in a loss of words at the moment. It's a crazy thing, but yeah, I'm gonna show you guys that and let you guys unfortunately see the car crash we call Quantum Eraser being a debunker now. Barney, you have no idea how much I appreciate the time for you to come and do this. Actually, I have some questions.
If you're going to leave and take this off air, just post the link to the Hangout so that people can come in, and if they have any questions or want to test something out.
Yeah, I'll start posting it in the chat right now. But I was gonna say, Hangout before I'm not gonna drop this one yet. But I'll make it silent, so if someone comes in, you guys can be talking. But when I'm done, I wanted to ask you a couple questions about the simulation, steps and all that stuff.
Sure.
Okay, so man, I'm forever in your debt. You have no idea how much I appreciate it. When we talking a little bit, we'll also talk about the next time, because we've got to be a next time. Because again, I enjoyed the crap out of it. I know a couple people were bored, but then again, a couple people, maybe they're not ready for this type of stuff. Chris? But yeah, hang tight. And again, man, thank you. Hey guys, I know a couple people asked me in the chat. Yeah, I'm gonna leave this up. I'm gonna put it in a couple. I'll probably put it in 3 different playlists. But again, Flat Earth, you guys should be upload the crap out of this and put it in your folders and realize that there's no deception here. If there was, what? Tell me what deception there was. We literally explained how this or shit. He explained how this. Barney explained how this works. It's you can't jump so many steps ahead just to disprove the people you're talking to, or you can't jump so far ahead that you're way ahead of the information you even have, because then you're not giving a good presentation for why you think it's this way. If you go ahead.
If any of you who have been watching, or anyone who will be watching later, has questions or needs something clarified, just post a comment below, tag me in it. I will try to come back and answer as many of those as I can.
Yeah, if I see any, I'll write them down too. I'll save them for you, and so everyone knows in the chat too. If you put them in my comments, I'll make sure he gets them, a whole 9.
There's nothing to hide. And also, if you have an idea how it might work and need to model it, need to run a simulation and don't know how to do that, talk to me. Like, I can either help you to learn how to do it, or I can help you do it. The whole point is, I'm not trying to disprove flat Earth. I don't believe that it's real. But hey, if you have some idea that works and gives the right predictions and produces better results, or you expect it to, right? Let's test it out. Let's try it out. Let's generate a model, let's generate the data, let's compare it to reality and see whether it fits and what needs to be done for it to fit.
Yeah, it's at this point, there's not Flat Earth saying there's no help, Flat Earth saying time. I mean, I know for a fact there are plenty of quote unquote Globers that are in my circle that are more than willing to sit down, respectfully talk to Flat Earthers, to either explain something they don't understand or go over whatever idea they have, and respectfully. It's this whole lying here and deceiving and all that stuff. It's, again, everything, whether it's what do I want to eat to where do we live and who's part of the deception. You need more than one observation, and you're not going to be able to make that that opinion about something based on insignificant data. It helps there, guys. All right, sir. I'm going to go ahead and end this one, and I'll be back in the Hangout in a second. I'm not even going to end it. I'm just going to mute it.
Okay.
All right. Thank you, sir. All right, people. Yeah, it's... Let me go ahead and mute myself so you guys can have a conversation. All right, guys. Like I said, this stream was... I did this stream for the opportunity for Bernie to be able to come on and present. The other thing I wanted to say is, at this point, because of last night, I'm no longer going to pussyfoot around this anymore. It's I'm not going to be disrespectful, because that just doesn't happen unless I'm triggered. But it's what I want out of all this. I don't really care too much about if I'm getting everything out information wise that is going to solve something, because I'm not here to solve anything. I'm here to learn something. But if you see someone who doesn't understand it, what do you think is better for all of us? What do you think is better for all of our truth? Them understanding it, or feeling disrespected and then just automatically going against it. Because a lot of what Flat Earth is doing is going against what the globe science says, what we're trying to explain on the realm of mainly all the disrespect that was happening in the past or happening from a group. And unfortunately, some of the people that just don't think that's necessary, like myself, like Barney, like a lot of people that I know, that disrespect shit doesn't need to happen. And then what ends up happening is and I've said this 1,000 times, I've seen it, and I understand 100% because I did it for 2.5 years. A flat earther is built up with a defense of, I know that glober is going to attack when. So that's why a lot of arguments are based the way they are. We need to think about that. Both sides need to think about it because it's ridiculous on both sides. And really look at the people that are making this content, and are they willing to veer off their narrative? Everyone's wrong. Why aren't these people wrong ever? And if they're not ever wrong, then shouldn't guys like Riley, Nathan, Bro Sanchez, like, shouldn't you guys be hitting me up right now to have Barney right here and hook him up with a simulation to prove how wrong the globe is? I mean, those are the ones that say they have all the information. They say they're never wrong. They can't be denied. Everything they say is gold. Everything anyone else against them says is wrong. Isn't that weird? Doesn't that say something? But hey, I want to save my rant for we're going to say 40 minutes now. 4:45, I'll be back. Again, Barney, thank you. Thank everyone that stuck around. Thank everyone that was really here to learn it and understand it and take those things in. I know there had to have been at least some flat earthers and globers that learned something and it stuck. Just the idea of what he simulated should open your eyes to what's needed to keep moving forward, to be taken seriously. But hey, I'll save that rant for later. Again, thank you guys. Appreciate it so damn much. Love you guys.